When we think of hypothesis testing, for me, it helps conceptually to think of the null hypothesis as being defended by Perry Mason, the famous defense lawyer who never ever loses a case. And that leaves you, the researcher with the alternative hypothesis, in the role of the poor, hapless prosecutor who's trying to argue that the evidence does not support Perry's client, that it doesn't support the null hypothesis. In a trial, everything is based on the notion that the defendant is innocent until proven guilty. The burden of proof is on the prosecutor. They need to amass enough evidence that the likelihood of the defendant being innocent is so remote that the jury concludes they can't be innocent. The same principle applies to hypothesis testing. Everything in hypothesis testing is based on the assumption that the null hypothesis is true. A fundamental rule of the scientific method is that we assume we are wrong. We assume that nothing is happening. We assume that there's no difference between the groups that we're studying. We assume that our treatment doesn't work. Now, in hypothesis testing, we look at the findings in our study and ask ourselves, what would we have expected to see if the null hypothesis were true? Are the findings consistent with what we would have expected if the null is true? If so, then we're forced to stick with the null hypothesis, and it's a bummer. In this situation, we say that we have failed to reject the null hypothesis, meaning that we're not saying that the null hypothesis is true, but we are saying that there's insufficient evidence for us to conclude otherwise. On the other hand, what if, based on what we would expect to see if the null hypothesis were true, the results appear very unlikely? In other words, let's say that we determine that if the null hypothesis were true, we would almost never have seen results like those that we obtained in our study. What would we do then? In that case, we conclude that it just seems so unlikely that we would see this if the null hypothesis were true, that the null can't be true. In that situation, we say that we reject the null hypothesis, meaning that we're not saying that the alternative hypothesis is true. We are saying that the evidence doesn't support the null hypothesis. We're saying that if the null were true, the chance of getting results so extreme is so remotely small that the null hypothesis can't be true. Well, is highly unlikely to be true. In time, if enough research continues to reject the null hypothesis, it's ultimately replaced, and what was the alternative hypothesis now becomes the null hypothesis for subsequent research. In effect, the alternative hypothesis becomes the accepted theory that research is then tested against. You can see this in this very abbreviated review of theories of gravity. Around the 4th century BC, Aristotle had his theory of gravity that said heavier objects fall faster than lighter objects. For millennia, that was the accepted, widely held theory of gravity. In 1589, legend says that Galileo tested this by dropping 2 different sized balls from the top of the Tower of Pisa. Now, whether Galileo actually dropped balls from the top of the Tower of Pisa is debatable, but go with me on this one. Galileo and others around that time conducted experiments and found that the data did not support Aristotle's model for gravity. They rejected the null hypothesis, and in time, Galileo's view for gravity became the accepted model and became the new null hypothesis. In 1687, Isaac Newton came along with his view for gravity, which was found to be a superior theory. So Galileo's model was replaced by a new null hypothesis, which was Newton's theory of gravity. That lasted nearly 250 years until Einstein proposed his theory for gravity, and in a beautiful test that used a solar eclipse to compare predictions based on his and Newton's models, the data failed to support Newton's theory, the null hypothesis, and based on numerous follow-up studies, Einstein's theory of gravity moved on to become the widely held accepted null hypothesis. But even now, physicists know that Einstein's theory isn't perfect, and new ideas are being proposed and tested, one of which will ultimately lead to Einstein's theory being replaced. In a way, all of that may seem a little harsh. Brilliant ideas by brilliant scientists get refined and rejected and replaced. But that's the nature of the scientific method. Now, of course, sometimes researchers will make mistakes. If you're my age, you may remember cold fusion or facilitated communication. In fact, if you think about it, there are 4 different ways that researchers can either get it right or make a mistake. You can see that in this figure where we're going to contrast reality, is the null hypothesis really true or really not true, with whatever decision the researcher actually made in his or her study. Did they fail to reject the null hypothesis or did they reject the null hypothesis? If the null hypothesis is not true and the researcher rejects the null, in other words, the researcher's right and they conclude that they're right, they've made the correct decision and are very happy. On the other hand, if the null hypothesis is true and the researcher fails to reject the null, their idea was wrong and they conclude that their idea was wrong. No one's going to go popping the champagne over that, but take heart in the fact that it was the correct decision. However, if the null hypothesis is true, but the researcher rejects the null, they've committed what is called a type 1 error. Researchers hate type 1 errors. It means they've sent everyone off on a wild goose chase. They're sending the field down a dead end. If you're Perry Mason, the defense attorney, this is your innocent client going to jail. Like I said, researchers hate making type 1 errors. It leads to people wasting their energy on ideas that are wrong or wasting their time on things that won't work, rather than putting their energy and time into things that will work or at least that may work. In practice, type 1 errors lead to schools spending money and resources on programs that won't help children, and children not getting the programs and services that actually will help them. Finally, if the null hypothesis is not true, but the researcher fails to reject the null, he or she's committed a type 2 error. This is really sad because it means that the researcher is in fact correct, but doesn't know it. However, it's not as bad as a type 1 error. Yes, it's unfortunate for you as a researcher, but at least you're not wasting everyone else's time and energy pointing them down a dead end. Thinking back to Perry Mason, this is the guilty defendant being found not guilty. No one likes it when that happens, but as a rule of thumb, Western society is more comfortable letting guilty people go free than innocent people go to jail. It's the same with the null hypotheses. Before wrapping up, I want to introduce 2 additional points regarding type 1 and 2 errors. The probability of making a type 1 error is called alpha. As we'll see in our next video, we choose our alpha, the probability of rejecting the null when it's true, before we ever begin our study. And in the behavioral sciences, we typically set this at 0.05, meaning we only want to commit a type 1 error 5% of the time. The probability of making a type 2 error is called beta. Now, this may get a little confusing because we'll have completely different things also called betas when we get into regression analyses, but you'll just have to keep them straight. Again, the probability of a type 2 error is called beta, and we typically want it to be around 0.20, more or less, depending on the nature of the study. That means if we're right and should reject the null hypothesis, we only want to fail to reject the null about 20% of the time. We want to conclude our theory was correct 4 out of 5 times if it is in fact correct. That point alone shows you that we hate type 1 errors more than type 2 errors, because we typically are willing to make type 2 errors about 20% of the time, but we only want to make type 1 errors 5% of the time. Now, we'll reference and use alpha a lot. For now, we won't spend as much time talking about beta, other than noting it's the probability of a type 2 error, but we'll spend more time with it when we talk about power analyses. So this will wrap up this video. The next 2 videos in this series describe how inferential statistics can be used to estimate how likely it is that a researcher is making a type 1 error. The researcher can then use that information to decide whether they're sufficiently convinced that they're not making the type 1 error to go ahead and reject the null hypothesis. Okay? Bye for now.